Okay. Be advised, if this is running, anything you say will be recorded. This is also going up online for those of us that aren't here, which isn't that many, but I would still prefer you to finish all your questions up to circuit analysis if you've not done it yet. I need to introduce to Kirchhoff's law. Kirchhoff was a fellow that did electricity a long time ago. He's one of the famous physicists that contributed to the development of electrical physics. He's got two laws that we follow. The first is the sum of any currents leaving a node in any electrical network is always zero. The way we actually say that is that what goes in must come out. If you put a 12 coulombs of charge through a wire, it goes in one end, 12 coulombs will come out the other end. That's what it's saying. And these are the laws that we use for circuit analysis. Kirchhoff's second law is, in any complete circuit, the sum of the potential differences equals the sum of the potential drop. Now the potential difference is going to be the amount of pressure, volts, that is behind any particular circuit. The volts add up to equal what the power source puts out. Now when you've got volts and it is applied to something, like water pressure to a sprinkler, the higher you turn the hose on, the more the sprinkler moves or sprays out. So in a lot of ways, when we do circuits, we use a hydraulic model of explanation as a analogy. I think I'm looking for. It's not a metaphor. Analogy. Yeah. So volts is normally equated to how much water pressure there is, and amps, so if we're dealing with Kirchhoff's first law, is often talked about as the flow rate of the water, like litres per minute, because amps is coulombs per second, and coulomb is an amount of charge, just like a litre is an amount of water. When we're dealing with circuits, we use specific diagrams. Now these come out of the Year 9 textbook. The degree to which you remember your Year 9 science is questionable, but that's irrelevant now because we can just review it all. This is a power source. So it's drawn with a long stick and a short stick. And the long one is the positive and the short one is the negative. So if we were to look at a power source, when you plug this in here, the red one is the positive and the black one is the negative. This is direct current. These are all direct current circuits, so the electrons are all flowing in one direction. This yellow one is an actuating current, so it goes backwards and forwards. That's what's in the wall, actuating current. That's why neither of them are positive and negative, because it goes backwards and forwards. Both of them are positive and both of them are negative. It just depends on which way the power is going and at what rate it's oscillating. But in the direct current, the electrons come out of the black one and into the red one. And in these circuits we got here, the electrons will come out of the small line and into the big one, because that's the black terminal and that's the red one. So they will be travelling in this circuit in a clockwise direction. Do I have any of them the other way around at the moment? No. But if I reverse those lines, it would go anti-clockwise. Of course, if you're a light globe, well, I can show you. Where's my stuff? Yeah. Here's one I prepared earlier. Now, if I get this and I steal the power from the projector, and give me a hand here, Oliver, because I wanted to get it on camera for those that you hold the power source up like that. Okay, we've got power. You're perfectly safe, I think. So now I don't know if we can just hold that up so the camera can see it. Actually, I can see the terminals here. So we've got the green wire coming out of the red one and the black wire coming out, the yellow wire coming out of the black one. Now if I turn it on, the globe turns on. No great surprise, you reduce the amount of volts, the globe gets less bright because you've got less water pressure. You increase the amount of volts, the push behind it, and the amount of energy, remembering that a volt is a joule per second, more energy is deposited across that globe. So if you stare directly at it, you can see it in your eyes, can't you? Now, I can change this So I can switch the wires around, turn the globe on. Any difference? Do you notice any difference? No. Alright. Now I put them in the actuating current. Any difference? Switch them around. Any difference? It's the same, right? Thank you. And that's because a globe is simply a piece of tungsten filament wire that's sitting across two terminals. So it's resistance wire. And when the electrons flow through it, they collide with the tungsten particles. Tungsten's a very hardy metal because when you're heating up lots, it is quite degrading at the microscopic level, and eventually that globe will snap, break, either through too much power, through the fact that it's burnt, or it's given off so much light that it's just had enough and it breaks. And they have filled the globe with an inert gas from, like argon or neon, so that you don't get oxygen oxidizing with the heat and the tungsten filament causing it to break. Remember what happens when people sleep in my class? Where do you have to go? Go to the study room if you need to sleep. You don't hang around in here. Right. So the globe doesn't care which way the electricity is going, but in all these circuits at the moment, they're direct current. You can indicate the volts on a circuit by just putting it up the top here, 12V. That means I've got that power pack set to 12 volts. And I know the electrons are going to go clockwise. Now if we look at Kirchhoff's second law, the volts add up to the equal to what the power source puts out. So how many volts are being dropped across that globe? 12. If I change it to 6 volts, how many would be dropped across the globe? What happens when you go from 12 to 6 volts when you're looking at that globe? It's less bright, isn't it? Just because you've got half the number of volts being dropped across the tungsten filament. So it makes sense that it's not going to be as bright. Now, that's a complete circuit. The circuit is able to flow. The current can flow, just like the water can flow. If it's not connected, it's not going to be able to flow. So if I cut it like that, literally it'd be like getting scissors and cutting the wire, then the globe will go out. So this is where we can add a little thing called a switch. And normally that'd be that little press button switch. You can get a variety of switches, toggle switches, etc. That's an open switch. That circuit's not going to flow. You can close the switch by doing the one like that. So that's your open switch and your closed switch. It doesn't always have to be a globe either. It can also be a resistor. Resistors are drawn like this. And you give it a certain number of ohms. 1000 ohm resistor. In this situation, what is the current that will be flowing in the circuit? Could you answer it? Absolutely. Whose law do we use? Not Kirchhoff's. Ohms. We want to solve for current, don't we? So I is equal to V on R. So I will equal 12 on 1000, which is going to equal, don't need your calculator for this. Is that it? 1, 2, 3. 0.0012, and the units? Amps. Hey. So we've already used Ohm's law to solve for that situation there. Now, in any circuit where the things are put around in the one path that it can follow, what do we call that? What kind of circuit is that? So that's with the letter S. Series. Series circuit only has one path. So the electrons can go around that way. If one of those globes blows, you've cut the circuit. The electricity won't flow. So a series circuit has everything in one path. Now when you're looking at a series circuit like this, if I've got one globe in the circuit like I had before, it'll grow really bright because 12 volts being dropped across it. What happens when I insert another globe and another one? Are they all going to be equally as bright? No, because you're passing through electricity through 3 different loads, which means you've got 3 points which are giving or converting the electrical potential energy into light and heat energy. And so all 3 of them won't glow as bright. You will drop 12 volts from here to here. If you get the voltmeter and measure from here to here, you're going to get 12 volts. But if you measure that one, or that one, they will all be less than 12 volts. Yet they will all add up to 12 volts because of Kirchhoff's second law. So that's a series circuit. Then you've got this option here, which is to have the 2 globes wired as such. What do we call this? Parallel. Now, that means that when the electrons come down here, they get to this point here and they're given 2 options. They can go this way, they can go that way. Both of those globes will have 12 volts applied to them. It's like having 2 sprinklers off a hose. You set the water pressure at a certain level, both sprinklers will be exposed to that water pressure. It does mess with the current, you know, because you're getting your flow rate through 2 different globes there. But when the electricity arrives back at the positive terminal, it will have dropped 12 volts because of Kirchhoff's second law. You can't have a 12 volt battery hooked up to something and have more than 12 volts. You have to convert the volts into a higher volts if you're going to do that. Which is of course possible. You can increase the volts and you can reduce the volts. That's what the transformers do. So if you go around, you look and you send them big ass boxes that are stuck to power poles, they reduce the amount of volts that is in the line down to eventually 240, which can then feed to your house. And the lines that come out of Channel Island, I think 144,000 volts. Really high level stuff. You can't connect 144,000 volts to your house. I mean, you can try. I wouldn't recommend it. But yeah, it's quite high. Now, you can also do a situation where you can have a series of globes in series and then another one hooked up in parallel to the circuit that's in series. And that adds an extra level of complication. Now the thing is, what happens if this globe dies?
Nothing happens. The eyes only.
Alright, so that globe's cut. Out of, let's call them A, B, C and D. We cut globe B. B blows. Which globes will light up?
They'll still light up.
Yeah, A, C and D will light up. Okay, A's killed.
No.
None of them will light up. D's killed.
No.
None will light up. C's killed. A, B and C, A, B and D will light up. So you need to be able to look at the circuit and imagine what's flowing and how it's going to work. Now, 2 of the things that we use to measure what's going on in a circuit, I mean, when we get around the circuit analysis, we'll use a multimeter. They're very useful. You just got this one unit. All you have to do is switch around the selection of what you want. If we have a circuit, I'll go back to a simple circuit here. Alright, we get a globe. How are we going to measure it? Well, we need volts to measure volts, and we need amps to measure amps. Let's add another globe just to make sure that we've got a difference here. When we're measuring volts, the voltmeter has an infinite amount of resistance. It's not going to let pretty much any electrons go through. A few will go through, but very few. So if you stick the voltmeter here, what's going to happen?
The light will it would just stop.
Yeah, just stop. It wouldn't work because it's got infinite resistance. It's important that it has infinite resistance because what would happen if I got a wire and I made the wire go like that? Would that globe light up?
Yeah.
No.
No. Ah, no.
What have I done to it? Short?
There's less resistance.
So that's the letter C, short. Circuit, yeah, you've short circuited it. Yes, electricity follows the path of least resistance. It always will. That's why when you've got the power in the wall there, he always looks sad, like a ghost face. Do you think he looks sad? I think he does. Because the eyes are like, oh. Anyway, that's the one that the power comes in and out of. That's the neutral, and that's the earth. The earth is important. Say, for example, this metal casing here, when I rewired the 1950s Van de Graaff generator, I've taken the earthing wire and I've actually screwed it into this metal casing. Now, if the 240 volts goes live on the metal casing and you touch it, and the only option for the current is to go through you, then it will. And you'll get a nasty shot, even might die. But if the current's given an option to go down a wire through to the earthing prong, remembering that wires have very little resistance because they're copper, it's going to follow the path of least resistance, it's going to go into the earth and not go through your body, because it will choose the path of least resistance. So that's the first and most basic safety feature that exists on many items. Question is though, how come we got items of just two? Yeah, I'll leave that here for the moment. Alright, so when we measure volts, we always put the voltmeter in parallel. Now, because it's got an infinite amount of resistance, the electricity is not going to short circuit through it. Consequently, you can measure the amount of energy dropped across that globe, but you're not going to short circuit it and use the voltmeter to chew up some of that energy. If the voltmeter gave off light and heated up, then some of that power is being spent on the voltmeter, and that's not what you want, because then you won't get an accurate reading. You want all the power to be spent on that globe. Now, an ammeter, on the other hand, an ammeter has very little resistance. If anything, none at all, because it's a flow meter. So what happens if you put the ammeter there? What's that globe going to do? Is it going to light up? Yes or no? Simple choice. No. Ammeter has no resistance. Electricity always chooses the path of? If you provide a path of least resistance, like an ammeter, it's going to go, woohoo, I don't have to get forced through this tungsten filament globe, heat up, and you know, it's not going to want to do that. It's going to go through the ammeter, because there's no resistance. So you've short-circuited with the ammeter. The problem with that is, you're probably going to find that it will dump a bunch of load across the ammeter and burn it out. So you never put the ammeter in parallel. You always put it in series. So now we have a voltmeter here and we've got an ammeter there. Let's put another voltmeter here, and let's put another ammeter here. We'll call this ammeter 1, ammeter 2, voltmeter 1, voltmeter 2. Now what's the difference between the reading on ammeter 1 and ammeter 2? Will they have a difference or they won't? Yes or no? No, they're not. Because remember, this is a hose, and there's only one path for the electricity to go around, because it is, ignoring all the things that are measuring it, at the end of the day, it's still a series circuit. There's only one path for the electricity to flow, and that's around the outside. So if you have the flow going in through here, and the flow going through there is the same because of Kirchhoff's first law. What goes in must come out. How about voltmeter 1 and 2? Will they be equal? Okay, we've got two no's. Damini is saying yes. What if I was to tell you that you're all correct? And also you're all wrong? The answer is it depends. If I replace them with resistors, so I know exactly the ohms, and I made that a 10 ohm and that a 10 ohm, they're precisely the same, 12 volt battery, then yes, the same current will go through them, V equals IR. If you're applying 12 volts to it, and they both have the same resistance, and we're going to have the same current. So the volts will be the same because they're also the same amount. Now, if I did this, okay, that's different. Which one's going to chew up more volts, the 30 ohm or the 10 ohm? Yeah, the 30. Okay, got more resistance. Was funny.
Whoever's making this basically.
That's awesome. When we were in tactics lectures at the Royal Military College, we had this big room, and in the middle was a big green sheet. And under the green sheet, they'd stick stuff, and it'd make mountains and you know, sort of terrain. And you'd lay out a road, and they had all these like wood tanks and things that represented troops, and they push it all around to teach you like to play out a mock battle. I was doing tactics as part of the training for officers, and you'd have your mate over the other side. No one's allowed to make any noise, and your challenge was to make them crack up laughing in the middle of someone's tactics lecture and then get them in trouble. It used to work really well. Before the lecture would come in, like the lecturer would come in, because they're always a military officer and they'd always be heaps more ranking than you. You don't want to mess around because you get in trouble. You all had to sit fast like this on the chair. It's more like standing to attention, but the sitting down version. And then the class would get handed over by the duty student. And so when you're all sitting fast, everyone's absolutely silent. Your challenge was to try and make your mate crack up in the absolute silence. I got it done a couple of times. It's awesome. It's like the pack rock. I've told you about the pack rock, haven't I?
Oh yeah.
So mean. I never did it to anyone. I did fill a mate's pack with leaves and rocks and sticks once before he was going to go home off a course, and he got to the airport and he put his pack through the x-ray and they started pulling out all these rocks and sticks, and he almost didn't get let onto the plane. He was so angry with me. Okay, so that's volts and amps and stuff. How much time we got? 9:40, 15 minutes. So why don't we go ahead and analyse the circuit? Let's do this one. We'll call this 30 ohms. We'll call this 20 ohms and 50 ohms. In fact, no, we're probably a bit too far at the moment. Let's do this circuit. 20, 40, 70 ohms. I've got to 955 now. Yeah. So this is a 12 volt circuit. And the power is going to get dropped across these three. So, noting Kirchhoff's second law, it's going to spend 12 volts across all three of those. Now we know V equals IR, yeah? So how are you going to work it out? Well, these are resistors in series. When the resistors are in series, we'll call this R1, R2, and R3. The total resistance will equal R1 plus R2 plus R3. So it's quite simple, isn't it? So you just add them together. So R total will equal 20 plus 40 plus 70, which equals 60, 110. Sorry, 20 plus 40 is 60. So yeah, 130. Sorry. So you got a total of 130 ohms. V equals I1. 12 equals I equals 130. Therefore, I will equal 12 over 130. Therefore, I equals something else. So we're going to work that out. We're going to calculate that. Oh, Dorito? I recommend at this point to keep all the decimal points. But we've got 0.0923, 07, 6923, so when you've got it on your calculator, keep them all in there so that you can just go up and select an answer again. Don't round off until the end, otherwise you'll end up with an error. So keep that there for the moment for me, Rudo. Alright, now that we know the amps, so say for example I put ammeter 1 there and ammeter 2 here, remembering that this is a series circuit, all the electricity will go around. Ammeter 1 is going to equal the same as ammeter 2. So ammeter 1 will read, ammeter 2 will read, and it's going to read 0.0924 amps. Great. But how much volts is going to get dropped across each resistor? Well, it's all going to be different. So you apply Ohm's law to each of these situations independently. The same current is going through all three. You got a resistance for all three. So V is equal to IR. So to work out the volts for that one, and that one, there's your I. Use the R that you've been given, you can work out the V. And at the end, if you know it's all correct, you'll be able to add up the volts across there, there, and there, and you will get yourself a completed answer. It's a bit different when we're dealing with a parallel circuit. If we're dealing with a parallel circuit, we'll call it R1, R2, and R3. To get the R total, because in the series circuit, R series, it's equal to R1 plus R2 plus R3 and so on, however many resistors you have in the circuit. In a parallel circuit, it's different. 1 on R total equals 1 on R1 plus 1 on R2 plus 1 on R3. So to work this out, let's say R1 is 20 ohms, R2 is equal to 40 ohms, R3 is equal to 10 ohms. So to work it out, it's going to 1 on R total will equal 1 on 20 plus 1 on 40 plus 1 on 10. Now, seriously, I've had people before go, well then that must equal 3 on 20, 40 is 67, 370. Literally, they wrote that in their test. I'm like, ooh, when was the last time you did fractions? You don't need to do them damn fractions. You literally put this into your calculator as 1 divide 20 plus 1 divide 40 plus 1 divide 10, and you'll get an answer. Which, Haruto? Oh, shit, you're quick. Oh, no, you're making me do it.
Yeah.
1 divide 20 plus 1 divide 40 plus 1 divide 10. So you get this answer, 0.175. You see, that's not the final answer, because 1 on R total equals that. So 1 on R total will equal 0.175. We need to rearrange this equation. So we switch those two. Therefore R total will equal 1 divided 0.175. 1 divided 5.714 285.714. I think that's repeating volts. So overall, when you stick those three together, you get a total resistance for the circuit of 5.714 volts. Because if you're applying a 12-volt battery to this, the amount of power that's getting applied to each of those resistors, that battery doesn't see 3 separate resistors. It just goes, I'm a battery, 12 volts. It doesn't give a shit what's attached to it, really. I mean, batteries don't think, but the manner in which this functions is it doesn't know. So you've got to do the calculations yourself. And again, thanks to Kirchhoff's second law, but also that water pressure thing, is that they're all going to have 12 volts applied to them. And you've got your 3 resistors there, but together they make, well, not a bunch of current. So when the electricity comes out here, ammeter 1, and then we add ammeter 2 here, what's coming out there is going to be the same as what's coming in there. But here, the electricity is going to split 2 ways, and here 2 ways, and then it'll all rejoin up as it comes back again. So if you put an ammeter here, an ammeter here, and an ammeter here, they're all going to read something different. Now if you put a voltmeter across the entire circuit like that, even you could do it like this, and it would still achieve the same result. What are those voltmeters going to read? Yeah, 12 volts, because they're measuring the load dump across all 3 resistors. But if you independently put a voltmeter across each of these circuits, so we've got a voltmeter here, a voltmeter here, and a voltmeter here, what are they going to read? 12 volts. Yeah, because remember, they're all applied with the same water pressure. I know the way I sounded was like it was going to be different, but it's not. They all got 12 volts. What changes is the current. So we can work that out. You can apply Ohm's law here. V equals IR. Then how do you work out the current? I equals V on R. Well, you have I. Do you? No, we don't, because the current's going to split. We know the current here and here, because we've got the total resistance and we've got the volts. But we don't know the current here, here and here. So to work out the current for this one, we've got to feed in what we know. Well, we know that it's going to be 12 volts because it's the same amount of volts that's dumped across each resistor. We don't know the current, but we know the resistance because resistor 1 is 20 ohms. So now we can work out an A. That's going to have a current, that's going to have a current. And overall, all 3 currents should equal what's going in. And it also should equal what's coming out. Yeah? Arigato. Darren book. All my books are at home, so that if we get shut down because one of you gets COVID, I can tell you what to do when I'm at home. If I don't bring it there, then I have to come back to school to the land of COVID and catch it. If I get COVID, I get COVID. At the end of the day, it's not going to stop me from partying. You are ready. You are ready, 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 ready. Circuit analysis. Read 69, 70. Yeah, haha, 69. 69 and 70. Read. Read 69, read 70. Do the questions on 85, 86, 87, 88, 89, and 90. So do circuit analysis questions. 85 to 90. So yeah, read 69 and 70 and do the questions from 85 to 90 for circuit analysis.